Okay. Hello, everyone. Let's start the section in this afternoon. And the first speaker is Professor Francisco Bushimi. He will give a talk on theory of quantum statistical comparison. Okay, please.
Thank you very much for giving the opportunity to present this talk at this meeting. So today I would like to give an overview on the theory of quantum statistical comparison, which is something that is very relevant for quantum resource theories, but it finds its roots in mathematical statistics, and it has applications in, we will see, it is a quite general framework to discuss like statistical or information theoretic problems. So the beginning of the theory of statistical comparison, so even before the quantum theory of statistical comparison, is the theory of majorization. So I'm sure that many of you have already seen this thing, but if there is someone that still hasn't seen the idea of majorization, I will briefly summarize its contents. So majorization is a pre-order that is used to essentially compare probability distributions. So we are given two probability distributions, P and Q. In principle, they need not have the same number of elements. You can always pad with zeros the shortest one. So we can assume without loss of generality that they are the same length. And then you reorder the entries of these probability distributions in non-increasing order. So from the largest to the lowest, to the smallest element. And you construct these truncated sums. So you will have a series of truncated sums for P. So you see that this index goes from 1 to K. So K will go from 1 to N. Okay, so you sum this element, the element of the probability distribution P, starting from the largest one, and then little by little adding the next one in the list. And you do the same for Q. And the definition of majorization is as follows. So you say that P majorizes Q, and you use this curly symbol of majorization whenever Pk, so the truncated sum for P, are always larger or equal than the truncated sum you get from Q. So you can actually draw this condition in this way. So you can put points here. So each line here corresponds to some probability distribution. And each point here will have these coordinates. So you have an x coordinate, which is kind of uniformly distributed. And the y coordinate is this truncated sum. So it's this kind of cumulative function here, pk. And you see that all of them will start from 0 and then in 1, 1, but some of them will be more curved than others. So, for example, you understand very easily that the minimal element of this preorder is the uniform distribution, which corresponds to the perfectly straight line that joins 0, 0 with 1, 1. So 45 degrees line, right? But why this is nice, this preordering is nice mainly because of a famous theorem by Hardy, Littlewood, and Poya that appeared in their book Inequalities in 1934, that says that this preorder of majorization is equivalent to the fact that there exists a bistochastic matrix M that transforms P into Q. What does it mean bistochastic? This is a matrix whose elements are all non-negative, and both sums over rows and sums over columns all give 1. So essentially, this matrix is a matrix that transforms normalized probability distributions into normalized probability distributions and keeps the minimal element, the uniform distribution, invariant. So the order of majorization has found a lot of applications in various fields of applied statistics and mathematics, from economics to information theory to a lot of things. And indeed, it was also extended, right? Because like a natural question was to see what is this thing for? Okay, what does it describe? So I would say one of the main figures to extend the order of majorization to a wider scope was David Blackwell between the 1940s and the 50s. So what did Blackwell did? So here is Lucien Lecam that essentially summarizes in one sentence. This is in the introduction of Lecam's famous book about asymptotic estimation theory. So he says the basic structures in the whole affair are systems that Blackwell called experiments and transitions between them. An experiment is a mathematical abstraction intended to describe the basic feature of an observational process if that process is contemplated in advance of its implementation. So this is a little bit complicated to understand perhaps, but we can see what it means. So first of all, let's introduce this object called statistical experiments. So the abstract formulation is as follows. So I give you a parameter set, omega, a sample set, x, and an action set, a. And then a statistical experiment or a statistical model, I would say that nowadays people use the name statistical model, is essentially a triple. So I have to give you a parameter set omega, a sample set x, and also a family of probability distributions on x labeled by omega. So essentially, you can also understand this in the case in which omega is, finite and discrete, as in this simple case. You can understand this as a conditional probability distribution. So then, what are statistical models useful for? So they're useful when we have to try to give an optimal solution to a statistical decision problem. So what is a statistical decision problem? A statistical decision problem or a statistical decision game, to use the word introduced by Blackwell, is given also by a triple. So now you have, again, a parameter set, omega, but now you have an action set and a payoff function, C, that takes couples omega A, pairs omega A into real numbers. So how do we interpret this situation? The situation is that there is some unknown parameter of nature, this omega. For example, omega can be a kind of bacteria, for example, a kind of virus, and you have a set of possible actions. For example, these actions could be a set of possible medicines or a set of possible antibiotics. And then there is this payoff function that essentially tells you how much you are going to gain if it is positive or lose if it is negative, if you choose some particular action A, so some particular medicine, in the face of the true value, true hidden value being some omega. Okay? So the point is that we do not have direct access to omega. And so we can instead construct some experiment that is able to give us some partial information about omega through this observable data X, whose distribution will bear some information about omega, because you see that this family depends on omega. So you hope that this dependence is as strong as possible. So how do you play statistical games with statistical experiments? So the idea is that the experiment, the statistical model is a resource. It is given, okay? So you can understand that you are going to use this thing that you can imagine it's a kind of tool that you have to spy on nature in order to try to have an informed decision about which action you should undertake later on. So how do you model this mathematically? Well, from omega to x, you go with a conditional probability distribution, but also given some x that you observe, you can decide a particular action A again by using another conditional probability distribution. Why a conditional probability distribution and not a function? Well, a function is a particular conditional probability distribution, but in principle, we allow for mathematical generality the statistician to also take randomized decisions. So in the face of the data, the statistician could always, for example, toss a coin and use the result of the coin toss in order to take her decision. So now, what is the expected payoff? So say that you are given an experiment, okay, to play some statistical game. How much you would be happy to pay for that experiment to be done? So there are various ways to quantify, of course, the amount of money that one is able to pay in order to increase the probability of a correct decision. This is one. So this is the expected maximum payoff. And it is defined as follows. So you see that here you have the conditional probability distribution from omega to x. Then here you have the decision that goes from x to a, and you sum over x and a. So summing over x, here you have a conditional probability distribution of a given omega. And then you take the expected payoff that you're going to get for each omega. And you take the worst case. So you're going to be pessimistic here. And you say, with some particular decision, what is the minimum payoff that I'm going to obtain? And then you can maximize later on over the decision function. So that's why it's a maximum payoff. And then the order that generalizes the order of majorization. So we understand also what majorization is about. Majorization is about comparison, like informativeness of a probability distribution versus the uniform one, okay? So the definition of information preorder is as follows. So now you have two experiments, W and W dash, and you have to choose between them. So of course, typically one experiment will be better for some decision problem, whereas the opposite is true for another decision problem. But let's say that W is always more informative than W prime. Okay, so what does it mean? It means that however you choose the statistical game to play, you should always prefer W over W prime. So typically this will not happen. So that's why this is a pre-order. It's not an order, okay? Typically you will find that two statistical models are just incomparable. So can we visualize this information pre-order a bit more concretely? And the answer is yes. And well, there are various kinds of this Blackwell theorem. In this 1953, there is a more general theory, but like in this simple case, Blackwell theorem tells you that this information preorder is equivalent to the existence of a conditional probability distribution that transforms this W into W prime for all Y and all omega. So just to give you a picture in terms of a circuit kind of drawing. So in black, you have the experiment W. So you have this unobservable parameter of nature that influences the statistical distribution of the sample X via this noisy channel, essentially. So Blackwell tells you that if W is more informative than W prime, then there exists a post-processing phi that is able to simulate exactly, to give you exactly the same correlation that W prime gives you. So essentially, you are able to build W prime using W. So this is a notion that sometimes is also referred to as statistical sufficiency. So W is sufficient, provides a sufficient statistic for W prime. Okay, and to go back to the connection with majorization, a very special case is when omega only contains 2 points. So you are comparing statistical models with only 2 elements, some P1, P2 versus another statistical model Q1, Q2. In this case, in the literature, sometimes there is the names dichotomy for this, to say 2 possibilities, P1, P2, Q1, Q2. So now how can you work out, of course, you can do calculations more explicitly because now you only have two elements. So in this particular case, Blackwell theorem gives you this recipe to compare dichotomies. So it tells you, first of all, construct these ratios, P1 and P2i and Q1j, Q2j, and relabel i's and j's in such a way that these ratios are non-increasing. So you start from the largest ratio, and then you go down to the smallest ratio. And now again, you construct these truncated sums, these kind of cumulative functions that now will be 2 for each dichotomy. So you have a truncated sum for P, a truncated sum for P2, and then you have a truncated sum for Q1 and a truncated sum for Q2. And you plot them as we did before in the majorization case. The difference is that now on the x-axis, you have points that are no more uniformly distributed, but are distributed somehow according to this cumulative function of P2. But still you can draw these lines. And again, this Blackwell preordering becomes essentially equivalent to majorization. Sometimes it's called like relative majorization because you say that P1 and P2 majorize the dichotomy Q1, Q2 if this Lorentz curve, this is the name of this line, is never below, the former is never below the latter. So this is the majorization, and Blackwell essentially tells you that there exists a stochastic matrix that simultaneously transforms both P in the corresponding Q. So now we see what was majorization about. Majorization was a comparison between two dichotomies, one dichotomy given by P and the uniform distribution, and the other dichotomy given by Q with respect against the uniform distribution. So that's why majorization captures the non-uniformity of a distribution, but you can have more general things like this. Okay, so this was, for example, used in quantum thermodynamics. This was called like thermomajorization, like 60 years after Blackwell theorem, but everything was already there in Blackwell theorem that studies classical statistical models, and in particular also dichotomies, then giving this condition. Okay, so let's see some quantum extensions for this. So in order, you can derive many quantum extensions, of course, but let's start from the, most straightforward one, which uses the formulation of quantum statistical decision theory given by Holevo in 1973. So here you have the notions in the classical case. So you have a decision problem, a quantum statistical model, a decision function, and then you have that max-min expected payoff C star G. I didn't write here because there is no room enough. What do you have in the quantum case? So in the quantum case, you see that decision problems are formulated exactly as they're formulated in the classical case. There is nothing quantum here, if you want. But now quantum statistical models are different. So now you don't have anymore a family of probability distributions, but now, of course, you have a family of density matrices. And the sample set is replaced by a Hilbert space, HS. And also decisions are going to be different. They are not going to be any more conditional probability distributions, but in most generality, you can consider POVMs, which stands for positive operator valued measure, which are collections of positive semi-definite operators summing up to identity. But just by replacing models with quantum models and decisions with quantum decisions, again, you can introduce this max-min expected payoff like this. So you see here you take this trace, and this is interpreted as a probability of having action A given value omega. And then you take average here, you minimize over omega, and then you maximize the minimum over all possible decision functions. So what kind of theorems can we get out of this formulation? So first, I need to introduce some simple notions. So first of all, test. What is a test? A test is something that is given with respect to a quantum statistical model. So I give you a quantum statistical model, rho omega. Then a family of operators ZA, Okay, I'm not saying any property for this data. They need not be positive semi-indefinite. They need not sum up to identity. But this family of operators is said to be an E-test, so a test for this quantum statistical model, whenever there exists some POVM that essentially gives you exactly the same traces than the ZE. Essentially, it means that on this statistical model, the ZE they give you the same statistics of a POVM. Okay, so because the model is not typically a complete set of states, okay, you don't have a complete basis to span the whole set of operators, you have to build some kind of equivalence class. So you can say that a POVM identifies some equivalence class in the set of tests for a given model. And then another definition is that of morphisms, which are like tests. They are a slight relaxation of the notion of positive maps, linear maps. So given two quantum statistical models E and E prime, so you see that the Hilbert space can change together with the states, rho omega versus sigma omega. And then a linear map from operators on HS to operators on HS dash is said to be an E to E prime quantum statistical morphism if and only if first N is trace preserving as a linear map everywhere. Then if and only if M is able to transform all rho omega into the corresponding sigma omega. And finally, if the trace dual map M daga maps epsilon prime tests into epsilon tests. So the direct map M transforms the rhos in the sigmas, whereas the M daga is again statistically well defined because whatever test for E prime you put in M daga, you get something that is a well-defined test for E. So now, given test and morphisms, we can see how does a quantum statistical comparison theory look like. So now I give you two quantum statistical models, E and E prime, and now we can define two information orderings that are analog of the classical information ordering of Blackwell. So the first one is this one that is exactly as the one in Blackwell. So E is more informative than E prime if and only if the max mean expected payoff from E is greater than or equal to the max mean expected payoff from E dash for all possible statistical decision problems G. But as you can imagine, if you have a little bit of intuition in quantum theory, typically you always need some kind of completeness sort of a notion in order to do things right, so to say, or satisfactorily. And indeed also here we need the notion of complete information ordering that we denote with this double majorization symbol here. So E is completely more informative than E dash if and only if E times F is more informative than E prime times F for all ancillary models F. So you see that this F is just some third quantum statistical model that I can use together with what I have. And so the idea is that it is not enough to compare E versus E prime, but I should also compare the performances of E with something else versus E prime with the same extra resource. And then we have some theorems. So the first theorem is that this information ordering, the simple information ordering, is equivalent to the existence of a quantum statistical morphism that maps from E to E prime, basically. So maybe you have already an idea what the second theorem will tell you. So the second theorem indeed tells you that complete information ordering instead is equivalent to the existence of a completely positive trace-preserving linear map everywhere. So a fully fledged quantum channel that transform rho omega into the corresponding sigma omega. And the third is a kind of link between the classical case and the quantum case, because it is possible to prove that if E prime is commutative, Okay, so you do not need both to be commutative models. Commutative model means this, okay? So that these states, the density matrices in this family, they pairwise commute. So only the second one need to be commutative. But if this is true, then complete information ordering is completely equivalent to simple information ordering. So that's why classically you do not need to consider any complete information ordering because everything already is given to you here. Okay, but somehow the operationally correct one to consider would be this complete information ordering, I would say, right? Why you should not be allowed to compare E versus E prime when you're given the same cyber source. Okay, seems very natural. Okay, so some applications of these ideas in information theory. So, for example, let's go back to the completely classical case. So we have been speaking about the idea of being more informative. So, for example, how to capture. So suppose that you have a broadcast channel, the black stuff here. So you have one input random variable and two output random variables, Y and Z. So how can we capture the idea that Y carries more information than Z? Okay, so there are various notions here. Of course, there is the notion of being stochastically degradable, which means to say that there exists a further post-processing that is able to process Y into Z. So that essentially, if you have Y in your head, in your hands, you can simulate Z as well and the correlations with X. Another possible ordering is that of being less noisy. This was introduced by Kerner and Martin in the 70s. That tells you this. So for all encodings here, so I have some message M, some other random variable M, and I consider all possible encodings of M into X. And now I say that Y carries more information than Z with respect to M for all such possible messages that I want to send. So whatever is the message that I try to transmit through this broadcast channel X, the receiver receiving Y will have more information because the conditional entropy is lower about the message than a receiver holding Z will have. And then there is a third notion, a notion of ambiguity. Okay, I made up this word, but it seemed plausible to me to call this ordering less ambiguous. So again, we are like Kerner and Martin. So we consider all possible messages that you want to send through your broadcast channel. And then you say that Y is less ambiguous than Z if the optimal probability of correctly decoding M from Z is greater than or equal to the optimal probability of correctly decoding correctly decoding M from Z. Okay, so this is the maximum probability that M1 hat equal to M greater or equal than the maximum probability that M hat 2 equals M. And this is really a reformulation of this Kerner-Martin ordering, because using mean entropies, you can see that this is exactly kind of mean conditional entropy ordering. So here the theorem works as follows, and it is essentially an application of the ideas of statistical comparison. So in 77, Kerner and Martin proved that degradable implies less noisy, of course, but the interesting thing was that vice versa instead is not true. Okay. Instead, one can prove that ambiguity is equivalent to degradability. So you can go back and forth here. And again, we see that this is a kind of statistical comparison pre-order. You can do the same with quantum broadcast channels. So now, again, look at the black thing. The black thing is the given resource. So I give you now a quantum broadcast channel, which is a channel with one input A and two outputs.
I have a question. So in the previous slide, what is your contribution and what is Kerner-Martin?
So Kerner and Martin is here, the left-hand side.
And also he proved the opposite and does not.
Yes.
Okay.
Yes. And my contribution is this one.
Okay, I understand. Thanks.
Okay. So you can do something similar also in the quantum broadcast channel scenario. So I give you a quantum channel with one input A and two outputs B and E. Now these are all quantum systems. And again, you want to give an idea that Bob has more information than E. Okay, so how can one do that? Again, this is just there are many ways in which one can consider this kind of question. This is one of them. So one possibility would be to say that the channel is degradable, so that there exists another CP-TP linear map that is able to map B into E. Okay, or one could, for example, consider the idea of Kerner-Marton, but like now upgraded to the quantum scenario. So now we also give the possibility of having a side channel that, however, I want to be fair. So I want to give the same information both to Bob and Eve. So how do I choose this channel? I choose this channel R to be symmetric side channel. So a side channel where essentially if you trace over S tilde, or if you trace over S, you have exactly the same CP-TP map. So this sometimes is also called the public channel, in case, in particular, the output state here is pure. In the literature, it is considered as the quantum public side channel, because it gives exactly the same information to the receiver and to the eavesdropper. And again, here I could say, okay, so I give you this channel, and I give you some kind of fair help to both Bob and Eve. And now I take any kind of classical message and I try to encode these messages in A and R. And then I ask Bob and Eve to decode. So I have a completely less noisy idea, which would be using the usual conditional entropies here. And I also have a notion of completely less ambiguous, which would be instead using this H-mean entropy, or to say really the probability of correct guess. So the probability that M hat is equal to M optimized over all the codings. So this is the theorem that we have. So now this is entirely ours, because of course, Kerner and Marton didn't have this quantum side channel, but somehow I would say that the interesting part is that degradability, quantum degradability now is equivalent to complete lesser ambiguity, how to call it, like being completely less ambiguous is equivalent to being degradable. Okay, so this is a kind of application in information.
Sorry, I have a question.
Yes.
I think in the quantum setting, Shun Watanabe considered similar problem, but he did not consider complete less noisy. He considered relationship with less noisy and degradable, I think.
Yes, he has a bit different definitions for less noisy. It is, if you check, this is more close to the original definition of Kerner and Marton. What Watanabe did was to consider, I think, so like some inequality between mutual informations, quantum mutual informations, I think, between Eve and Bob. But I think Watanabe using a definition that is very similar in spirit to Kerner and Marton, but is a bit different.
Okay.
And anyway, he's interested then in asymptotic distillable key rate or asymptotic quantum capacity, and he's looking for a larger class of channels that have single letter formula, if I remember correctly. So here instead we are kind of looking at degradability conditions. We also have, it is possible also to apply these things in open quantum system dynamics, but I don't have so much time. So let me think. Maybe I will go through this and then instead I will skip through the final. I don't know, what is more interesting, open quantum system dynamics or quantum thermodynamics? I ask you. What you prefer to hear? Masahito, what do you prefer to listen about?
Thermodynamics.
Thermodynamics. Okay, so let's go to thermodynamics. Okay, so because this Blackwell theorem was used for what people call thermomeasurization, then a natural idea would be, okay, so let's use the quantum Blackwell theorem in order to characterize quantum thermomeasurization. So the idea is that you have two states, rho and sigma, and you want to understand when you can go from rho to sigma with some idea of thermal operation. Okay, so I will see later what we mean by that, but the main idea, so the starting idea here is that, okay, so why we don't consider the comparison between two quantum dichotomies, rho and gamma versus sigma and gamma, where gamma is the thermal state. The thermal state, I mean some state that is given by some Hamiltonian, some temperature, and then you construct the Gibbs distribution according to these two objects, okay? So why we do not consider the problem of thermal accessibility as a problem of comparison between rho and gamma versus sigma and gamma? So we have two main problems here. First, the first problem is that unfortunately, Blackwell theorem for dichotomies does not generalize as well to the quantum case, in the sense that apart from the very, very, very special case of qubits, so when the dimension is equal to 2, for which you can really essentially draw these Lorentz curves, quantum Lorentz curves, and everything is in there. If you go to dimension 3 already, that's not enough. There are counterexamples that tells you that you need some kind of extended comparison. So how can we give a kind of physical notion of this extended comparison? But not only. Another problem is that Gibbs preserving channels can create coherence between energy levels. So if I only look at these two dichotomies, the problem is to transform rho into sigma, keeping gamma invariant. The problem is that these channels, which are called Gibbs preserving, can create coherence between energy levels. And people say that this is a problem. So how can we manipulate a thermal operation in this way? So the idea is to consider, so first of all, to turn a dichotomy into a channel, okay? A kind of classical quantum channel. I gave these channels a name like on-off channels because essentially you put some input in them and then they measure. If the input was 0, the output will be thermal. So I imagine some kind of laser in the off state where the radiation emitted is thermal. And instead, if the input is 1, then the output becomes this rho, which is not thermal, okay? And you can input possibly kind of superposition between these two states. Okay, so you have a channel now, you make a dichotomy into a channel, and now you can consider this kind of problems. So a problem that is about distilling a singlet state, a singlet fraction. So before, you remember that there were these problems in which Alice and Bob had to guess correctly a classical message. Here, it's a bit different. So here, the idea is to apply a decoding after the channel in order to maximize not a guessing probability, but a singlet fraction. So this is a maximally entangled state. And here you have some mixed state to start with. Okay, so then there is this theorem that I proved that given two quantum dichotomies, E and F, so you see now that rho2 and sigma 2 can be actually different, okay? So they need not be thermal. So let an E and an F be the corresponding on-off channels. So here you put the channel, this classical quantum channel, and then there exists a post-processing of E into F if and only if the singlet fraction you get from E is always better than the singlet fraction you get from F for all possible omega. So essentially, the game now is defined by the initial mixed bipartite state. Okay, so this solves the problem of extended comparison, but it doesn't solve the problem of coherence. So for the problem of coherence, we had this paper in collaboration with Gilad Gur, David Jennings, Rung-Yao Duan, and Imam Mardian, 2018, in which we essentially what we do, we take this thing here, and we notice that this is very convenient if you also want to put some kind of covariance condition because of the maximally entangled state here that allows you to do, I call it the ricochet trick. So to move a unitary operation on the other side, okay? So then essentially what it means that, okay, let me give you this slide and then I will stop. So for two quantum dichotomies, rho gamma and sigma gamma, and this group, so what is this group? You see here there is the logarithm of gamma. So gamma here is the thermal state. So essentially this is the Hamiltonian, okay? And then here you have the parameter t, which is time. So this is the one parameter group of time translations generated by the system Hamiltonian. So we write that this dichotomy E is completely more informative than F with respect to this group G, or T maybe, this is probably a T because time. If and only if there exists a CPTP linear map that transforms rho into sigma, keeps gamma invariant, and it is covariant for this one parameter group of time translations. So now, these are not what people call incoherent operations, unfortunately, because in particular in the many copy case, you can have degeneracies between equivalent representations, and within those equivalent representations, your channel might create coherence. But in the single copy case, this is exactly equivalent to incoherent operations. And moreover, it has a very strong physical meaning because essentially this tells you that these games are kind of synchronization processes, right? You want to synchronize your system here with another reference in a way that it is time invariant. So it has a good physical interpretation, I would say, even though we don't get exactly what people mean by incoherent thermal operations. These are like time covariant thermal operations, which I think it's best, but other people disagree. Okay, so conclusion. So the theory of statistical comparison studies morphisms, which is to say preorders, of one statistical system X to another statistical system Y. What I mean by statistical system, anything that has a statistical meaning, like a statistical model, a noisy channel, a quantum channel, a bipartite state. So depending on your scenario, resource theoretic scenario, you have some meaning of this statistical system. Then equivalent conditions are given in terms of finitely or infinitely many monotones, like this. So this is exactly like the core of the theory of statistical comparison. The theory of statistical comparison is the theory that tries to find monotones that characterize preorders. And such monotones then naturally quantify the resources at stake and the operational framework at 10. For example, the expected maximin payoff in decision problems, or the information asymmetry for broadcast channels, or the joint time energy information for quantum thermodynamics. So if you want to take home one message, just say that the theory of statistical comparison essentially studies morphisms and monotones between resources, statistical resources. And with this, I finish my presentation and I thank you for your attention.
Okay, thanks for the interesting talk. Any questions or comments?
So, sorry, I have some question.
Yes.
About the quantum thermodynamics part. In that part, you consider this is somehow related to modularization.
Yes, yes.
That kind of discussion also similar time done by Margot Mametcher's group, I think. Do you know?
Could be. Well, I have a paper with Marco, right, in which we consider quantum dichotomies.
He did not consider dichotomy, but by using this kind of modularization, he derived that a kind of second order analysis.
Oh, I see. You're not for dichotomies then.
No, but somehow he consider he used this kind of
Idea.
marginalization relation. So this is somehow essential in his paper.
Okay, thank you very much. If you maybe can send me the link on the chat, or maybe I can search for it on the archive.
Yes.
Thank you.
But he did not consider dichotomy, so this is somehow difference.
I see.
But somehow dichotomy means, in order to consider dichotomy, we consider pair of densities, rho gamma and sigma gamma.
Yes.
He also considers similar things, so he considered rho tensor omega and sigma tensor omega.
Oh, I see. Okay. Thank you.
Thanks.
Okay, I would like to continue the question whether it is equivalent to when you consider the quantum dichotomy.
Yes.
I changed the epsilon as rho tensor gamma, and the F is written as sigma tensor gamma, and then
I don't know. Here, one really considers the two separately.
Okay,
you know,
because here you, with the same gamma, you will fix the operation, right? Because then you just allowed the operation that keep gamma invariant.
Yes, exactly. So gamma gives you kind of a kind of point constraint.
Okay.
And satisfying that point constraint, you have to find a channel. That's the problem in quantum thermodynamics, essentially.
Okay, thanks.
Welcome.
Okay, I would also like ask another question.
Yes, please.
Well, when you establish the equivalence between completely less noisy and the degradable, if I remember correctly.
Yes. Classical case?
The next one, I think.
Okay.
Yes, here, here M means that it is classical information, right?
Yes.
So why do you use classical information? And well, because another option
in the paper we used
quantum, right?
Yeah. So the paper here is a bit early, right? It's 2014. So at the time, I discovered this kind of theorems with a classical input. But then later on, 1 year later, I understood that you can do the same with also a quantum input, right? Something like this. Okay, you see that this is 2015, so it's 1 year after. So now, a posteriori, I can tell you that you can derive a similar result also with a quantum input, where then you have to distill singlet. The problem there is that if you have Alice and Bob, Bob and Eve, they cannot both distill a singlet with the reference at the same time, right?
Yes.
It becomes, the entanglement is monogamous. So then it doesn't have a very beautiful interpretation, I think. But maybe, one should think again about it now, and maybe it is possible to give a better interpretation. Because here the thing can happen at the same time, right? So simultaneously, you are a sender, you encode the message into some part A and some part R. R gets splitted like fairly. equally
Yes.
between Bob and Eve. And then all like information asymmetry would be here in the given channel. So this you can do like one shot, like, you know, you put M is encoded, and then Bob gets these two output, Eve gets these two output, and they have to guess what was the message. So
Yes.
in this sense, it has a nice, it seems to be some kind of related with the rate of secret key distillation, right? Because somehow Bob has an edge over Eve in getting correlations with the sender. Unfortunately, this is only in the guessing probability scenario, so it doesn't lead to a non-zero rate necessarily in the asymptotic setting.
Yes, I know it, and well, I understand that why you can, but if you, I mean, is it possible that you compare, I mean, compare the payoff function, for example, use the fidelity, then you need not to require that, well, the all M1, it will recover the singlet, but just to recover a state that is more close to a
Okay.
singlet.
I don't know. Yes, it's an interesting question. Maybe, you know, if you're interested in these things, we can keep discussing later on.
Okay, thank you. So
Thank you very much.
I think the time is
Okay, so I will become the chair, right?
Yes, use the next chair.
Okay.
Okay, thank you very much. Thanks.
Okay, so I stop here and I take on the role of chair for the next session. So the next speaker is Jiawei Wu. Are you here? Okay, can you share your slide? Okay. Let's see if it works.
Okay. Can you see it?
Yes, very well. So you can maybe start. I can see the PowerPoint.
Okay.
Okay, so start. Let's see if you know. Okay, perfect. Okay, so the next speaker is Jiawei Wu from the Department of Physics of Tsinghua University, and he will tell us about private dense coding framework. Please.
Okay. Thank you for inviting me to speak at this workshop, and I will introduce a work collaborated with Masahiro Hayashi. So in this work, we propose a framework of private classical communication using quantum state and quantum channel. In this framework, we will apply the quantum web type channel theory, and we will improve the finiteness secrecy bound. The finiteness secrecy bound was achieved by constructing a practical linear code for a practical linear code, and this can be implemented efficiently. First of all, we know the dense coding was an interesting phenomenon because we can transmit 1 qubit by we can transmit 2 bits of classical information through 1 transmission of a qubit. Some variants of dense coding can be quickly constructed. If we have perfect entanglement and noisy channel, then this is the setting of entanglement-assisted classical communication. The capacity of this setting is very famous because it can be singularized. We can also have the case of noisy entanglement and noiseless channel. In this case, the capacity is also very simple. Also, the intrinsic properties of quantum channel provides us the power of secure communication, since a quantum channel can always be treated as an interaction between the state and the environment. For example, the private capacity of a noiseless channel and a perfect entanglement is exactly 2. So based on these simple settings, we want to construct a more general setting to cover most of the private communication scenarios associated with dense coding. Now, we allow Alice and Bob to share and also Eve to share general states. It can be entangled or decoupled. They are connected by a noisy channel, gamma. To send messages, the transmitter Alice is allowed to apply a unitary operations, and the unitary operations should compose a group. Then she sent these encoded states to Bob through this noisy channel. We denote such a setting with 3 elements: the pre-shared state, the allowed unitary operations, and the noisy channel between Alice and Bob. In this case, we will assume that Eve is so powerful that she can intercept the state by Alice, sent by Alice, through a noiseless channel. This is our worst case. This is also common. This assumption is also common in quantum K distribution. So our goal is to explore the secure transmission rate in this setting. Our requirements are, first of all, the reliability. It requires that if the protocol does not abort, Bob should recover the message with a large probability. The secrecy requires that the information leakage should be small, and the completeness requires that in honest case, the communication should abort with a low probability. Our secrecy criteria is defined as a trace norm. This is also the same in the quantum K distribution. Then through our setting, we can construct 2, or in other words, this communication can be treated as a wild-type channel. Exactly, to be more specific, it is a classical quantum wild-type channel. The channel 1 is the channel 1's input is the choice of this group unitary, the elements of the group. It is the operation of Alice. The output is the state received by Bob. The second channel its input is also the group elements, and the output is the received state by Eve. Since this is a noiseless channel, so it is not affected. To analyze this scenario, we will apply quantum wild-type channel theory. Intuitively, if a channel is stronger than another channel, then the secure communication should be possible. The achievable rate is defined as that for this rate, there exists a series of codes such that the decoding error probability goes to 0, and the information leakage also goes to 0 as the coding length goes to infinity. The first condition should associated to the completeness condition, and the second condition associated to the secrecy. The capacity is defined as the supreme of all possible achievable rates. The capacity of quantum wild-type channel is already a known result. However, this form cannot be evaluated effectively in the general case. So our goal will be a more simple but not tight achievable rate we will achieve this rate with our constructed code later. First of all, we have the asymptotic result for our setting. This is a simple application of the above achievable formula. However, if we have this special condition, that is, this state is maximally correlated and the pre-shared state is pure, then this achievable rate becomes the capacity because it is a degraded channel. Then we have our modular code construction for the CQ wild-type channel. The code is a concatenation of inverse universal hash function and a arbitrary error correcting code. I should note that this error correcting code is not specified. It can be any error correcting code, and we have no assumption on its linearity or something. Then using this modular code construction, we can get a finiteness bound, secrecy bound. First, I should introduce the universal hash lemma. That is, if we have a classical quantum state and a universal hash function family, and we apply this this function on the classical L, then we have this trace norm, a bound on this trace norm. It is bounded by this sandwiched Renyi conditional entropy on this original state. And this can be transformed into a more easily understandable form as this. Here we use the information leakage to denote our previous defined secrecy criteria. This is the sandwiched Renyi mutual information, which is connected to the conditional entropy, and this term is the sacrificed length of universal hash function. The above bound is for the one-shot case. Then in the n-fold case, we have a more simple form. So in an n-fold symmetric channel, we define this sacrificed rate R2. Then the symmetric condition should reveal a connection between this quantity and this quantity. The difference is that this mutual information is evaluated on the L set. Maybe I should recall that L is a set before the error correction code encoding, but it is connected to the mutual information on the input set of the channel. That is, this quantity has no relation with what the error correcting code looks like. So we have this bound. We have a more simple bound on the information leakage. This can be evaluated without knowing the structure of the error correction code. And this bound has an improvement on the exponent term. We can see that if we fix this sacrificed rate, then the decreasing exponent is this form. However, the previous result using the previous universal hash lemma, it differs in the 1 plus t and a 2 term. So this decreasing speed is more fast. Also, our reliability is guaranteed by an error verification process. The error verification is done through by applying a universal hash function to our message. Then we got the abstract of our message. And after Bob decodes the message, he also applies this universal hash function, and Bob should compare these two abstracts. If they coincide, then Bob accepts this result. Then, or Bob should reject, and the communication should abort. This guarantees that the received message coincides with a large probability. Applying the above result on quantum web-type channel to our private dense coding framework, we got the performance of our protocol. The first is the completeness. The completeness relies on the performance of error correction code. This differs in different cases. The second term is the secrecy. This is connected to the pre-shared state. And the third term is the reliability. It is connected to our universal hash function used in the error verification process. We can apply our private dense coding framework to a typical example. In this example, the allowed operation of Alice is the generalized Pauli operator. And the pre-shared state can be generated by sending a Bell state through a Pauli channel. And Eve is the environment. In this example, we can have a direct picture of how the transmission rate and the secrecy goes. The first picture shows that with the channel, this is the channel parameter, because Alice and Bob is connected through a depolarizing channel. And this is the transmission rate. R1, R2 are the error correction rate and the sacrifice rate. R is is R1 minus R2. So R is the final information rate. This shows the asymptotic performance, and the second picture shows the finiteness performance. In the finiteness case, we can see how the error correcting rate, the sacrificed rate, and the rate sacrificed for the error verification goes. After we got the code length of about 10 power 5, that is a 100,000 length, the rate should achieve almost achieves the asymptotic rate. Also, we can construct a practical linear code according to our code construction. It requires that the unitary group should form a vector space over a finite field. And the Bob's received state should commute with each other. Then this can be constructed with a linear code and can be efficiently decoded. In the case of the unknown pre-shared state, we should perform some test on the state. In general, it is we need to do a complex test to measure many parameters. But if we apply a discrete twirling operation, then this the pre-shared state can become simple, and the times of measurement can be reduced to a low number. So to summary, we propose a general private dense coding framework, and we propose a modular code. In this modular code, we improve the file-length secrecy bound, and this can be realized with a practical linear code. The parameter estimation method for a high-dimensional unknown state is also given. Oh, thank you. This is the end of my speak.
Thank you very much for your presentation. If there are some questions. So I would like to ask you something, but I mean, it's very trivial.
Okay.
Could you show me again the definitions of those quantities, like I with the down arrow?
Okay, I have this. I have a page showing these quantities.
Okay. Thank you.
Can I ask a question?
Yes,
Okay.
please.
Okay, I wonder whether the the rate is relevant with the shared tripartite state tau ABE.
You mean how the rate is related to the
Yes,
pre-shared state?
because you restrict the encoding operation as a coherent group, right?
Yes.
Group, a unitary group, and then I wonder that if the encoding operation is restricted to the unitary group, then for some state, for example, for separable state between A and B, then this kind of encoding cannot provide any advantage. Then you just and it's better to discard the separable bipartite state than just use the quantum channel to send the information.
Do you mean that this pre-shared state is between Alice and Eve?
So you assume that there is a bipartite state, rho AB, between Alice and Bob, right?
This state is shared between Alice, Bob, and Eve. This is a
yes.
pattern,
And
yeah.
yes, and if the reduced state if the reduced bipartite state AB,
yeah,
of this tripartite state is separable. I mean, it is possible that the bipartite state is separable. Then
yes, it is possible.
yes. Then if the encoding operation is restricted to unitary operation, I wonder, a better way to transmit information with such a shared biparty state is just discard the biparty state and just use the channel.
It depends, because I did not assume this tripartite state is pure.
Yes.
So there is a possibility if we assume a simple situation that Alice and Bob share a classical random k-bits, and this k-bits has no relation to Eve state. This is also included in our case, in our framework.
Okay, see. So you mean that the tripartite state is not pure?
Yes.
And not restricted to pure. So it.
Yes.
Okay. Okay. Thank you.
Yes, thank you.
Any other questions? Okay, if not, I would like to thank the speaker again. And maybe we can, so the next talk's going to start in 4 minutes from now. Maybe we can start to share slides to see if it works correctly. Thank you very much. Okay, perfect. So I will wait 3 more minutes.
Hello, can you hear me?
Yes, very well.
Oh, okay, thank you.
Thank you. Okay, so the time has come. It is 3:50 here in Japan. And so it is my pleasure to introduce the next speaker, Professor Harumichi Nishimura from the University of Nagoya. whose talk will be Power of Distributed Quantum Merlin-Arthur Proofs. Please.
Thank you. Finally, thank you for inviting me to give a talk. The title is this, and also this is the joint work with Pierre Freignaud and François Rugal, and I'm Paz. This talk is about the distributed computing, which is several computer, and these computer are connected wires, but these are all distributed, and the task is to solve some problem. For example, leader election and Byzantine problem, like several. This is a difficult task because the computer is distributed. So usually, if the problem is trivially easy to compute, for like diameter, if the central node the only one computer, but this problem is difficult if the computer there are several computers on the network. 20 years ago, almost 20 years ago, some Tani-san and Benoit et al. Studied the quantum version of distributed computing. This is one more work, but in this case, we consider the not distributed computing, but distributed certification. This is like this kind of task is like polynomial time algorithm, but this is NP verification. This is the outline of my talk. First, I introduce the problem and setting. After that, I give a result and give an overview of our protocol. Our problem is very simple. This is the equality of data. So the network has several nodes called terminal. Terminal has the data, very large data, for example, X. The problem is this terminal has same data or not. All data identical or not. This case is yes, because 3 terminal has same data. On the other hand, this case is no, because this guy and this guy has different data. This is a difficult problem for distributed computing, which means that we need the omega R round are needed to compute this problem. Here, R is the diameter of network. So the distance, maximum distance of the 2 terminal. Of course, one round you can send the message to a neighbor. So to reach both data, some intermediate node, we need the almost diameter around to compute. So the this trivial lower bound is exist. Here in this talk, we don't assume any private and shared randomness or entanglement. But this problem has the very simple NP-like protocol, distributed certification. Now we move to the setting distributed certification. we call the distributed Merlin-Arthur protocol. Merlin-Arthur protocol is a exactly probabilistic version of NP protocol. So this guy is a prover. It's usually the computationally unbounded, but untrusted. On the other hand, another guy, verifier, sometimes called Arthur, want to check some property, but less powerful. For example, polynomial time. For example, the NP problem, a given number, large N, is composite or not. This has the NP-like Merlin-Arthur type protocol. Because if N is composite, verifier can check it easily by receiving a non-trivial divisor as certificate. For example, this number has the non-trivial divisor. So this guy, verifier, can check this dividing this value to this value. On the other hand, if this value is prime, for example, 251, it's a prime. This case, this guy send any message, verifier check the 251 divided by the message. It is easily checked. It's not composite. So verifier always reject. This is the NP-like protocol we call Merlin-Arthur protocol. Now we consider the distributed version of this protocol. The difference is the verifier part. So now verifier consists of the network. So not easily communicate each other. This in the literature, the several name has proof labeling scheme or locally checkable proof, etc. But we call this in this talk distributed Merlin-Arthur protocol DMA protocol. In this case, the certification protocol has two phases. First, prover phase. So prover sends certificate to each node. The second, verification case phase. This case, the verifier checks the proof by exchanging the message with neighbor. This is, we consider the only one round protocol. So the each node can send a message only the neighbor. This is the distributed Merlin-Arthur protocols. The property is similar to NP. So if the problem is yes instance, then all node verifier accept. If we consider the probabilistic case with high probability. On the other hand, no case, some node reject, and this node alert it's illegal. So this some part is the different usual NP protocol. So specific to distributed case. Now I introduce the DMA protocol for the our problem equation equality of data. It has trivial protocol. First, prover send X when all data are X. So initial state, this terminal has only data and this white node does not have any information. Then prover send X. Then the verifier, each node check its same by exchanging the message with two neighbor. So this guy send message to neighbor, and this guy also to message neighbor. Then every node know neighbor's data is same. So everyone accept. This is a completeness. On the other hand, if some node has different data, this is no case. This case, every message, this case, prover send X. So this edge is different data. So the checking stage, this two node alert the reject. But even if any other message, some edge has different data, so some node reject, no case. This is a very trivial protocol of our problem. But this is inefficient protocol because prover send the message, if message has n bit, prover send n bit to each node. Usually distributed computing, the message must be logarithmic or polynomial of logarithmic of data. So this is not allowable for efficiency. Now we move quantum version of DMA protocol and present the result. Our result, we consider the quantum version of Merlin-Arthur protocol. So the now prover can send a quantum message to each node, and each node can exchange the quantum message to neighboring node. We consider this DQMA protocol, but first we observe the classical lower bound. Our problem, equality of data. Any DMA protocol require omega n bit certificate. So previous trivial protocol is optimal in the order. Of course, error is reasonably small. On the other hand, our protocol has a small certificate in terms of the length of data. So this part is the, our advantage. So the message certificate length and the length of message is log n plus r times t times r square. Here r and t is the parameter of graph size, but usually the data size n is much larger than graph size. So our result is superior to classical case. This is our result. Now, I move to overview of our protocol. In fact, our protocol important part is the network is pass case. Pass is the very simple network. Now we have two terminals, the left end and the right end, and the path length is R. So this case is R is 1, 2, 3, 4, 5, 6. And this case, we consider the X equal Y or not. First, we consider the two-node path. So R is 1. This case is efficient protocol exists in classical case. And also, we don't need prover because we can use the hash function. Hash function satisfy these two property. First, if X is not Y, then the hash value is different with high probability. And the length of hash function and hash value is logarithmically small. So this guy just sent, this guy choose randomly a hash function and send hash function and hash value. This is efficient length. And this guy create the hash value of Y and check the equality. That's it. Now we consider the three-node case. This case, similar strategy is impossible because we consider only one round case. So this guy sends the message to central node, but cannot send to right node directly. But this guy can send something. For example, this guy choose randomly a hash function and hash value is sent to central node, and central node can take something. In fact, this type of communication is similar to simultaneous message passing model in communication complexity. This is well studied in communication complexity, introduced by Andy Yao in 1979. This guy has data, and also another guy has different data, and check the equality. This guy. This is completely similar to the three-node case. In fact, the unbiased show the upper bound of this equality function root n. So we can reduce the communication to root n. But also, this is the lower bound shown by Nissan and Segeri and Babai and Kimmel. So this strategy is also limited, not efficient, because the efficient protocol must have logarithmic of n. Now, how about the DMA case? Previous case, we don't consider any prover. Now, if we consider the help of prover, for example, this guy sends the hash function and hash value, and this central node to send message to both ends. this seems work. No, because prover may malicious. For example, hash function maybe not randomly chosen. Our classical lower bound is a simple combinatorial argument. This is the certificate size. Prover certificate size must be linear in N. Even the path length is 3, so the 4 node case. Now we move to quantum MA protocol. In this case, the similarity of 3 node case and SMP complexity. So we can use this old result by Berman-Cleve Waterous dwarf. This case, quantum case, 2 guys can send quantum message. This case, equality can compute it only logarithmic message. So exponentially improvement by quantum communication. This is similar to the 3 node case, so we might be able to use this argument. Now we remember the Berman-Cleve Waterous dwarf important tool. First is quantum fingerprint. This is the superposition of the hash function and hash value. This satisfies the orthogonality of 2 different hash fingerprint. Namely, if X is not Y, then 2 fingerprint is almost orthogonal. And the second trick is famous swap test. So X equal Y, then fingerprint is same. On the other hand, X not equal Y, fingerprint is orthogonal. So swap test can check whether it's orthogonal or not with high probability. And also the message length is short. So this strategy is directly usable by in the case of 3 node. So just left end send the fingerprint of his input, also right end. And central node check the swap test. But this trick cannot directly use if the length is more than 3. So we need to consider the sum. Now, our protocol, I show our protocol. Our protocol first prover phase. Honest prover. This guy, when X equal Y case, honestly send the certificate of fingerprint of X to each of intermediate node. So this input and this input is now yes case same. So the other central node receive the fingerprint. And verification phase, we check the equality by swap test. In fact, each node J choose the random value, binary value, and if value is 0, then the J send the state to right neighbor. Otherwise, this guy keep the fingerprint. This case with probability 1/4, at least 1/4, some node can check the left neighbor and this guy has same fingerprint or not by subtest. And if subtest is failed, subtest failed, then node is reject. Node reject. Now we move analysis. If the two data is equal, then the previous our protocol in our protocol all node accept with probability 1. This is almost trivial because all intermediate node has same fingerprint. So any coin flip, the check is succeeded. On the other hand, X is not equal Y, so two input is different. Then the probability that all node accept is 1 minus 1 divided the length of line square. So this probability can reduce to, for example, 1/3 by protocol or R square repetition in parallel. So this type protocol is done in parallel, still one round protocol. So the important is that if two data is different, the probability that all node accept is 1 minus 1/R square. To show this is the technical part. In fact, this means that we want some node to reject subtest with probability 1/R square. To show this, we use this property. Subtest accept on input entangled state in row AB with high probability. Then to reduced state row A and row B. So trace out other part must be closed. This is our technical property. If this property hold, then all nodes accept with high probability. Then most left finger close to row 1 and row 1 close to row 2, etc. And this reduced state close to right node fingerprint. So left node fingerprint close to right node fingerprint, which contradict because left fingerprint is almost orthogonal to right fingerprint. This means some node must reject high probability. That's our argument. This is a line graph case. Now we can extend the line case to general graph using standard method of distributed computing. In fact, general graph case, prover sends the rooted labeled tree with fingerprint like this. For example, this case, prover sends the fingerprint, this plus the rooted tree, spanning tree. So this part is root, and this is a child of the root like that. And root has root is terminal. So this guy has input A, and the terminal also has input for each X, Y, B like that. Now, run the protocol online previous from the root to terminal in parallel. So for example, this part is consider this red line and run the protocol to line case. Also this other case. Then we, of course, all input A, B, C, D, something are all same. Then protocol accept with probability 1. On the other hand, if some part is different, for example, A and B is different, then this line catch the difficult, not the data is not equal with some probability, say 1 over R squared times graph size. So we can this protocol repeat in parallel again to improve the soundness. Now I summarize our result. We introduced a quantum version of distributed Merlin Arthur protocol, where quantum certificate from prover and quantum message among nodes. Then we can show a protocol for equality of data with logarithmic size qubit certificate and message in terms of data size. But we have extra parameter depends on graph size. On the other hand, classical case, any protocol require linear size of data certificate if error probability is reasonable. In fact, we can extend to more general protocol, which converts the one-way quantum communication protocol. It's a kind of in communication complexity protocol. This can be converted to our setting. And we can provide efficient protocol for any function. If this function has efficient protocol in one-way communication complexity, then DQMA protocol, we have efficient DQMA protocol for this function also. But this converting is only line graph case. Now, I summarize my talk by future work. First question is there any DQMA protocol better than DMA in terms of graph size parameter? So sometimes graph size parameter is very important. And some distributed computing problem has no data, but the graph itself is the input. In that case, graph size parameter is very important. So it's very nice if you can find a quantum Merlin Arthur protocol better than classical case in terms of graph size parameter. And second question is, of course, the trivial quantum lower bound. We show only the upper bound, so just give the efficient protocol, but we don't know any lower bound. So if you have any lower bound using some information theoretic technique, we appreciate. That's the end. Thank you very much.
Thank you very much for your presentation. If there are questions from the audience.
So I have a question. So somehow I usually consider the opposite situation. So somehow prover, there is several prover and only verifier is one.
Yes.
So this is I think more usual, but you are saying prover, the number of prover is one, and
Yes.
there are so many verifier. So, but your discussion looks like it depends on the topology of graph of prover.
Yes.
Somehow quite complicated. So because, for example, in the case of opposite situation, usually people do not consider that kind of topology. Only we consider a number of prover, for example, 2 or 3 or something.
Yes.
But so that kind of so complicated topological structure of verifier is so essential in your discussion.
Yeah. In fact, the distributed Merlin Arthur protocol study is the topology of the network is very important, and the network itself is the kind of the input. For example, the network has the bipartite graph, bipartiteness, or the 3-colorability. This is a kind of the problem. This is a trivial if the node has only one, like the usual interactive proof. But the verifier is distributed. Such a problem is not non-trivial. So the distributed.
I could not understand. That means that if the graph is so simple, so in that case, the problem reduced to the single verifier case.
No. Even the graph is not simple like the line case.
Thank you.
In this case, the left node and right node can send directly message, cannot send message directly as in this talk. So the problem is not non-trivial anymore. So,
For example, if we have two verifier, so then you have some improvement.
we don't consider the, any multiple prover because in the literature, in classical case, there is only one prover. So,
No, prover one and verifier is only two. So in that case, there is
of course, verifier is only two, which means just the two node and maybe the two nodes are connected.
Yes,
This case is much simpler, and this case is maybe the almost trivial.
Trivial means that there is no improvement from
because if in our setting we can send message one in one round. So essentially, the two node case is no difference than one node case.
No improvement. So what is the minimum structure to improve conventional case?
So the three node is already the difference, I think. So in our our problem, data is same. Left node and right node is already the three node case. Quantum case is efficient protocol, but maybe classical case does not have efficient protocol, even if
efficient means that somehow non-trivial improvement, significant improvement over.
That have significant improvement, I think. So because in fact, three node case, this case, we have central node. So both guys send fingerprint and check the subtest. This is efficient protocol, even if there is no prover. But maybe even if there is a prover, classical message case need more than root n length, I think. So classical case and quantum case is have much difference even in three node case.
You consider this line node?
Yes, line node.
So if we consider somehow a complete graph with three nodes, in that case we have improvement over the single node case.
I think three node.
Only three node case, three node complete graph, or this line graph case. Only two cases with three node.
So maybe if complete graph, you can the message you can send message to one node, then that one node have all the data. So this guy can compute anything. So in general, complete graph case is no difference single node case in one round communication setting, I think. So this type, some node, some pair is far in the network. This is very important to show such this type of superiority. For
So in this
example,
okay, okay, now I understand. In this problem setting,
yes,
the existence of pair of nodes that are not directly linked to each other.
yes, yes,
That kind of pair of node is very important.
yes.
Okay, I understand.
Okay, are there any other questions? Okay. If not, I would thank Professor Nishimura again and all the speakers of this afternoon session. And I will close. This is the end for today, right?
Yes.
Masahito? Okay.
Yes.
So the meeting will continue tomorrow from 9:30 in China and 10:30 in Japan with the talk of Professor Legal about the quantizing the quantum singular value transformation. Until then, I wish you a good afternoon and a good evening, everyone. Thank you again. Goodbye.
Thanks. So now we have a free discussion time.